Section 8.2, area of surface of revolution. When a region bounded by curve is rotated about the line, a solid of revolution is generated, like this. The lateral boundary of such a solid of revolution is the surface of revolution, like this. When we have a line like this and rotate it, then this generates this type of cone. Then this surface area can be found as this, as you see. Okay. In this case, if you have a cylinder like this, then it's just simply computed by 2 pi r times the height h. And if you have a cone like this, then as we see, a sector of a circle with radius L and the central angle theta is 2 pi r over L. Therefore, the lateral surface area A of this cone is 1/2 times L square times theta. Okay. So we have the pi times r times L, like this. And theta, when the theta is here. Okay. Then think about the small piece of this cone like this in figure 3. Observe that each of the lateral surface of a circular cylinder and the circular cone is generated when a simple polygon is rotated about the line. Okay. For example, in figure 3, let us find the lateral surface area of a portion of a circular cone with slant height L and upper and lower radii Ri and R2. Here L1 and L2 and Ri, R1 and R2. It's radiuses. It is found that by substituting the area of a smaller cone from the larger cone, as shown in the figure 3, the surface area of this can be found with this. So all we have to do is find the bigger one and subtract the smaller surfaces to get the surface area of this object. Then the slant, in figure 3, the slant heights are proportional to the radii, so we can have the relationship like this. So R1, RL2 is same as R2, L1. So the slant height L of the first term is L is equal to L2 minus L1. So this is the L, and the bigger radius is R2 and smaller radius is R1, and this is L, which is the subtraction of L2 and L1. Okay, then the surface area, this pi R2 L2 minus pi R1 L1 can be simplified in this way by adding and subtracting the R1 since Ri's and Li's are proportional, R1, L2 and R2, L1 is same, so we can just add and subtract, and then this can be factored like this, so we can write A is equal to pi times R1 plus R2 times L. So we obtain the surface A as A is equal to pi times R1 plus R2 times L, which is the length between here. So the surface area in that case can be found as 2 pi RL, when R is equal to the medium of R1 and R2, which is the average radius of that band. Okay, with the we can think one more thing from there. Suppose we consider a problem of finding the area of the surface of revolution obtained when a smooth curve y is equal to f of x on the interval a and b is rotated about the x-axis like this. Suppose you have y is equal to f of x like this on the interval a and b, rotated to have this type of object. In figure 4, then assume f is positive and has a continuous derivative. We divide the interval AB into n subintervals with endpoint x0 and xi and xn and equal widths delta x. And if yi is equal to f of xi, then the point pi lies on the curve. So we divide it as intervals like this. Okay. Then the part of surface between xi minus 1 and xi is approximated by the band obtained by taking the line segment pi minus 1 to pi and rotating it about the x-axis. As n increase, the approximation gets better. So the band has the slant height L and average radius R, like this. So by the equation, the surface area can be obtained in this way. 2 pi RL, 2 pi RL, 2 pi RL. Then we have, and also, as we also already showed that this length of the line can be approximated by this with the mean value theorem when xi star is some number in this subinterval. And then delta x is that when delta x is small, we have yi as f of xi star when xi is star is the number in the interval, in subinterval, and yi minus 1 as okay, and yi minus 1 can be approximated by f of xi stars. And at the end, since f is a continuous function, therefore we have this form, figure 5, like this. As you see in the figure 4, we find the area here and rotate it to find the surface area like this, and add all of those to have the revolution of the surface area by curve. We are looking for the surface area of each of them and adding all. Okay, here. So the earlier equation can be approximated by 2 pi f of xi star times square root of the line integral that we have found, have shown already before. Okay, then if we just then add all of those with the summations and then take a limit process as n goes to infinity, the Riemann sum for the function g of x, which is this, can be written in this way. So limit sigma can be written as an integral, and the d delta x can be written as dx to have the formula, which gives us the formula for finding the area of the surface of revolution obtained by rotating the curve y is equal to f of x on the interval a and b about the x-axis. So s can be written as integral a to b 2 pi f of x square root of this times dx, or with respect to okay, and this f prime of x can be written as dy over dx. So we have the formula with these observations. Okay, 2 pi y square root of 1 plus y prime square dx. Or if we have an equation x is equal to g of y on the interval c and d, then the area of surface revolution obtained by rotating the curve with respect to the y-axis becomes this. Okay, integral from c to d 2 pi x square root of 1 plus x prime square dy. 여기, okay. Symbolically, for the rotation about the x-axis, the surface area is this, and for the rotation about the y-axis, can be written in this way. So 2 pi y ds, integral 2 pi y ds, or integral 2 pi x ds, where we use for ds either this or this, depend on the axis that we choose to rotate. Okay, that's it. That's it. That's it. Then we have the rotation with respect to axis in this way, and rotation about the y-axis in this way to find the surface area of this curve after the revolution. Okay. So we now have the formulas, so we use it to find the real surface area in the problems of example 1. Determine the area of the surface of revolution obtained by rotating about the x-axis the curve y is equal to sine x, when x is in between 0 and pi over 2. Okay, here, this is actually, when you have a sine of x, and this is a rotation of that function with respect to x-axis, that can be drawn in this way, and then y is equal to, then we use the formula to find the answers like this. Okay, 2 pi, integral from 0 to pi over 2, so y equals sine x, so 2 pi sine y here, and since y is equal to sine x, so the y prime is cosine x, so here cosine square x there, 1 plus cosine square x can be that we can integrate it in many ways. Okay, and we can simplify with the substitution of u is equal to cosine x, and then we have this, and we may use just integration by cos tool sage to get the answer of this one, or we just do the computation with the formulas or by hand to get the answer of this for this surface area like this. For the second example, determine the area of surface revolution obtained by the rotating about the y-axis, the arc of the parabola y is equal to x cubed from this point 0, from the origin to 8. Then we can draw the graph of this function y u cube like this, and then we use the formula s is equal to integral 2 pi x ds, where y is equal to x cubed and y prime is 3x square. So we have 2 pi integral from 0 to 2 x times square root of 1 plus 9x fourth dx. So we just use the sage command to get the integral of this. So from here, by substituting 3x square as u, then we have a simple form of integral like this. Then we just use the sage code to have the integral of this function. The square root of 1 plus x square from 0 to 12 to times the pi over 3. Then we're going to have 98 pi, which we can have it like this. So yeah, we just use this formula to have the answers. And in the process, when we need to do into the integration, simple integration, we can use Sage code. Yeah. By other substitution, yeah, we can have the same answers. This code was saved in here, so you can practice it. Yeah. Next, example 3. Find the area of the surface of the sphere of radius r, positive. Then we use the formula. So in order to do so, we need to have the function y is equal to f of x or x is equal to g of y. So in this case, the equation of the upper circle with radius r and center at 0, 0 can be written in this way. It's a circle. Okay, so we have square root of 1 plus y prime square is equal to this. So the desired area of surface, which is x is equal to 2 pi from minus r to r, square root of r square minus x square, which is y, and square root of 1 plus y prime square is this, times dx. So this is so these two are simplified. So this is a simple integration of 2 pi integral from minus r to r dx. So r is a constant, so this can be easily found as a 4 pi r square. Okay, yeah. So with the Sage code, we have the same answer as 4 pi r square. Example 4. I think that's the last example in this section. 4. Find the area of the surface obtained by rotating the curve about the x-axis. The function is y is equal to x plus cosine x from when x is in the interval 0 to pi. So if we draw the graph, then we can easily draw the graph of x plus cosine x and the revolution of it like this. So we wanna find the equation. We wanna integrate the 2 pi y times square root of 1 plus y prime square from the integrated from 0 to pi with numerically, that gives us the answer like this. So yeah, you may find the exact answer, or you can use the numerical value of the integration in this way. So you can use those codes for other problems in the exercise in section 8.2. Here is just some code and was introduced, so you may use those codes to draw the figure of the function in the problem and to do the integration with the formulas that you have here. So that will help you to solve the most of problems in section 8.2. I think that's it for section 8.2. Any questions?